So,
So,
this is going to be a little different from my usual videos. I wanted to do this for a while. Do kind of videos that are unscripted, off the seat of my pants. Try to be as accurate as possible. It's going to be videos where I just talk about whatever I want. Anything really. Science, video games, fucking Warhammer 40k.
that's the one.
But the big thing is they are going to be unscripted. So if I just start rambling, hopefully I'll cut it out in editing, but maybe not.
I can maybe stop you. I can try. But
You can try.
I can try.
And I'm going to try to be as accurate as possible about the information I'm talking about, but I am human. I am not writing a script for these, and I will not blatantly say something that is untrue, but if I think something will be more entertaining if I say it in a way, or it'll be easier to understand a model that isn't 100% accurate, I'm going to do that. With that out of the way, First fucking topic. Oh, one more thing. I'm probably going to release 4 or 5 videos all at once, and after that, I'll try to do one a week. If I don't make it, my limit is going to be a month between videos at most. So, without further ado, the first video topic, the goddamn periodic table of elements. Now, before you leave, because I know this is giving you flashbacks to high school, and nobody wants that, there is actually a lot of very interesting information that can be gleaned from the periodic table of elements. First of all, the weird ass fucking shape has a purpose. The shape of the periodic table tells you what kind of general properties that element will have and what you can expect it to look like and do. For example, we'll start with the first row, first column, and that is these green boys right here. Those are the alkali metals. Ignoring hydrogen. Hydrogen is its own beast.
Its own weird beast. Does whatever it wants.
It does whatever it wants. The alkali metals explode with water. These guys are highly reactive. So something to note about the structure of the periodic table is it is built row by row like you're reading a book. And what the row tells you is how many electrons each element has. And as you go from left to right, the atom gets more electrons. And once you get to the end on the far left, it has a full outermost shell. And then once it fills a shell, it starts a new shell, and it starts filling that shell with electrons. So, just by the number of rows, there are 6 shells in total that we know of. And I'll get to that later in a little bit. So, hydrogen starts with 1 electron, and you go all the way over to helium. Helium has 2 electrons. But now helium has a full shell, so you go to lithium. Lithium now has 1 electron in its shell. So the big thing about the alkali metals is they all have 1 electron in their outermost shells. Now the thing to know about atoms on the periodic table is they very much like to have full shells. And when you have 1 electron difference, it is very easy for that atom to get a full shell. The alkali metals just kick that fucking thing out of there. They kick it out like a parent who's done with their kid's shit and won't move out after college.
Like a lion kicking his cub off a cliff. Get out of here.
And that is why these guys are so explosive with water because water has a lot of oxygen in it. And the oxygen is like, yeah, fuck yeah, I'll take that electron from you. And they just boot that shit out of there, which releases a lot of energy and can create some very explosive results. Like that one guy who faked cesium in a bathtub with a grenade.
Oh.
Did you ever hear about that?
No, I did not hear about the cesium grenade.
No, there's this one video I remember because I watched it in high school. And I bet so many people watched it in high school, where this guy was doing a video on like the alkali metals and how reactive they are in water. They chucked some sodium in, it like lit up, burned a little bit, and then like the poof. And then like potassium, they chucked a bit of that in. It was a little bit bigger. And then they put rubidium in a bathtub, and it made a pretty big boom, like it threw water everywhere.
Why do you go rubidium with air quotes?
Because I'm pretty sure they didn't actually use rubidium. I think they just put an actual explosive in there. And so
Science.
And so when they went to do cesium, they put cesium, a capsule of some cesium in a water-soluble capsule.
Probably sugar.
Probably an actual fucking explosive and not cesium. So, because like the guy who's like running the program, whatever it was on, he was like, so what's going to happen when this cesium touches the water? And the scientist they had on set was like, imagine a depth charge. And they were like, okay, and went and chucked the thing in and ran behind a blast shield. And I think it was later revealed that they actually just threw an explosive in there and detonated it. That one was weak. Oh shit, this is on. Oh well.
Yeah. I was like, do you have a cool wallpaper you could put up or something? You're like, nah,
that's
fine.
what you were talking about.
Audacity, running in the background. I'm like,
You meant up
yes. No, I meant on your computer monitor.
So yeah,
it's a hand-grenaded bathtub. Goes boom.
Yeah, I'll try to find a clip of that. Because like I'm pretty sure it was revealed that they faked it, and they didn't actually put cesium in there.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does.
Which makes sense, because cesium is really rare to get, and so it's kind of expensive.
It's pretty far down on the periodic table.
Yeah.
Right? The stuff near the top is usually more common.
Yeah,
right?
stuff at the top is very common. Stuff near the bottom, like physicists that want to be chemists make that shit.
Right. Some of the stuff they probably make with the collider, right? They just slam two smaller things.
Well,
like
even francium down at the very bottom of the alkali metals does occur naturally in nature, but because its outermost shell is so far away from the nucleus of the atom, I haven't even talked about how atoms are structured. So like
video.
No, I'll do it right now. Atoms are structured. They have like They have a little nucleus in the middle. It's made of protons and neutrons. Protons have a positive charge. Neutrons hold everything together. So basically, as you get bigger, you get more protons. Same thing as the electrons in the atoms, actually. You get one proton for each position you go. So like hydrogen has one proton. Helium has 2 protons. Fucking carbon has 6 protons. Yeah, so you got your protons and your neutrons in the nucleus in the middle. And then you got, like, electrons in the fucking...
Shells
around it. So basically, the further...
Hey, that's carbon.
The further... yeah, it is carbon. The further shell... No, that's boron.
No, that's...
5 electrons. 1, 2, 3, 4, 5,
There's 6.
6,
That's
7.
oxygen.
Oh, it's... Yeah. No, it's nitrogen.
It's oxygen. Wait.
nitrogen.
Oh, yeah, nitrogen. Oh, okay. You got
nitrogen.
I couldn't see that pair.
So basically, the more shells you have, the further away the electrons are from the nucleus. And the positive charge of the protons attracting the negative charge of the electrons is what keeps the electrons in. So you can imagine the one electron in francium's outermost shell being pretty far away from the nucleus. That thing will just fucking leave on its own sometimes. So francium can occur naturally, but it is very rare to find it in its atomic state with the all the electrons it should have. It's also extremely reactive. I think the very small amount of pure atomic francium we have is kept in like some lab in France somewhere. That's why it's called francium. And it's in like this sealed container, and it's filled with some kind of unreactive...
like a noble gas, probably.
I don't even think it's a gas. I think it's some kind of unreactive liquid.
Oh, okay.
Yeah, it might just be... I have no idea. It might be a liquid noble gas. I cannot remember.
You can do that? You can make liquid noble gases.
Very fucking cold. Like,
I guess we have helium.
Yeah,
for
NMR.
Yeah.
Helium is like a liquid. I think at like a couple degrees above absolute zero. So yeah. Okay, so that's the alkali metals. Explode in water. Very reactive. Kick that fucking shit out of there. The next stage.
Hit the road, Jack.
The next column are the alkali earth metals. Don't ask me what the fuck makes them earth metals. I have no idea.
They're from Earth. Like everything else on this periodic table.
No, everything on this periodic table is from the stars.
Oh, right. Yeah. Except for these ones. They're from Earth, which is from the stars.
So these guys are a lot like the alkali metals, except they got to get rid of 2 electrons to have a full shell. Some of them are just as reactive, maybe a little bit less reactive. Of note are calcium.
Strong bones.
Strong bones.
Strong bones.
Calcium
Bone man.
milk. Get strong bones. And the other one is magnesium, which
burns brighter than the sun.
Yeah.
Don't look at it. Isn't magnesium in like road flares and shit?
Yeah. Yeah, not much to say about them. Basically, anything I've said about the alkali metals can be said to the alkaline earth metals. The next is this big blue block here. Those are the transition metals. And just like their name, we're going to transition over them. Just joking. They're all the fucking metals you can think of. We got titanium, we got fucking iron, cobalt, nickel, copper, zinc, gold, platinum, palladium, silver, mercury.
How come gold, the symbol for it, doesn't have like any of the letters in gold in it?
Because all the symbols are based off of fucking Latin.
Oh, okay.
The dead language Latin.
Right.
because scientists just fucking love giving things Latin names.
Yeah.
That's why every single species name you've seen for any animal is fucking unpronounceable. So yeah, these guys, being an organic chemist myself, these don't get any fucking use. The only use these have is like transition metal chemistry, which is like throwing things onto transition metals as ligands. They can make explosives, I guess. They're very useful as catalysts, particularly palladium.
Aren't some of them reactive? Is thorium on there?
We're gonna get to that.
Okay.
And then you got this green section here. Those are also metals, but for some reason they didn't get the name transition metal. Probably because they're underneath gases.
Right.
This blue section in between the green and the red, those are metalloids. They have properties of metals and non-metals and kind of separate the two. And they're boring as sin.
Hey, silicon's pretty cool.
Yeah, silicon is cool. There's an idea. So, silicon is in the same column as carbon. When you hear that all life on Earth is carbon-based, that is, all organic matter it's mainly made of carbon. Like, all organic matter is made of organic molecules, which is just various chains of carbon with other shit bonded onto it, usually hydrogen, sometimes oxygen, phosphorus, sulfur, in the rare occasion a halogen. So since silicon is in the since silicon is in the same column as carbon, and it can also make 4 covalent bonds, just like carbon, it is theorized that silicon could possibly also be used as the skeleton for life. However, silicon doesn't make long chain structures like carbon does very well. So it'd be very hard to get a DNA like a molecule like DNA out of silicon. Because it needs to be so fucking long.
If you take DNA out of the nucleus and just like stretch it out, isn't it like football fields?
Yeah.
More like multiple
These things,
tens of football fields.
Imagine a single atom. You've got like fucking trillions upon quadrillions of atoms could fit in that one tiny little fucking dot right there. They are obscenely small. And then a single DNA molecule is like, I don't know, something like 20 carbon atoms in like a couple ring structures. And then it's just chains and chains of that. And then, so that minusculely small structure, over a football field long, is the amount of DNA you have in one cell. It's wild.
And silicon can't do that. It can't go that long.
No, silicon can't make chains as long as carbon does. For some reason, once it hits a certain length, the instability gets too high and they just break for some reason. But it is possible. Very unlikely. So past the metalloids, we have in red, we have non-metals. And they're not called gases because carbon isn't a fucking gas. Everything else is. Except for sulfur. Sulfur's weird. Sulfur also stinks.
Yeah.
so
Weird
carbon,
stinky boy.
We got carbon, that's the thing of life. We have nitrogen, that is the atmosphere. 70% of the atmosphere is nitrogen gas, probably more. We got oxygen, the thing you need to breathe to live. I think the atmosphere is something like 19% oxygen gas. We got phosphorus, stuff that can glow, also war crimes. Sulfur, that is in shit and volcanoes. Literal shit, like feces.
Demons smell like it.
Demon smell. There's actually neat thing about that is feces and decaying matter, like dead shit, releases chemicals called thiosulfurs. And we have evolved specifically to be able to smell that and know that shit is bad.
That is either shit or dead shit, and that shit's worse.
Yes. Orange section, right here. We got the halogens. These will fucking kill you.
Yeah.
These are mostly gases. We got fluorine, chlorine, bromine, and iodine. They will fuck your shit up if you breathe them in.
Chlorine gas bad.
War crimes. Chlorine gas is a part of the mustard gas they used in World War I to commit war crimes against the French. Probably deserved it by being French.
If they didn't commit war crimes against the French would have committed war crimes against the French.
Yeah.
But why are they so bad to breathe in?
Because just like they are basically the opposite of the alkali metals. The alkali metals have one electron in their outermost shell. My dog is here.
Doggy.
Hang on.
Yeah, you should grab her.
Come here, Piper.
Dog.
This is my dog. Her name is Piper. She's a border collie and she's almost 4 months old. And she's a very naughty girl who chews on everything. Yeah. Especially my shoes. Okay, go.
Shoe gremlin.
So the alkali metals have one electron in their outermost shell. They want to get rid of it.
Right.
The halogens have almost a full outer shell and are missing one electron. Right. They really want to get that electron. So they will rip that electron off of anything to get it, including the cells of your lungs. Generally, if you get halogen gas in your lungs, the best thing you can do is find God and kiss your ass goodbye.
Pray to whatever God you believe in.
Pray to whatever God you believe in, and if you're an atheist, well, fuck you.
You'll find a God. Pretty fast.
You better find him.
Even if it's the Emperor.
Fluorine, you might recognize as similar to fluoride, the stuff that is notably in mouthwash and toothpaste. Right. That is a big difference. This fluorine is the fluorine atom, which really wants an electron, and so will rip molecules apart to get that electron. Right. Fluoride is the ionic form of fluorine, which is fluorine that has found that electron. And it is happy now and unreactive and kills bacteria for some reason.
They don't like happy things.
Yeah. Chlorine is also notable for ripping a hole in the ozone layer. Yeah. What can you do?
Carbon chlorine.
Yeah.
Well, bad.
Chlorocarbons. Right. Chlorofluorocarbons. Organic molecules with chlorine and fluorine. Really fuck up the ozone layer. But we stop using them, and the ozone layer is healing.
Yeah. It's healing. Self-healing.
Okay. So this purple section on the very end is the noble gases. And as you've probably guessed, since it's on the very end, they have full outer shells. And because their outer shell is full, they are very happy, extremely unreactive, and won't do shit. But that does not mean they are not useful. Helium, for instance, goes in balloons. It makes them float, because helium gas is less dense than the air around you.
We all float down here.
We all float down. You'll float too.
You'll float too if we fill you full of helium.
Neon, if you run an electric current through it, fucking glows pretty colors.
Neon lights.
Neon lights. That's why they're called neon lights, because they're actually neon. They also have a function of, like I mentioned earlier with francium, you can submerge an extremely reactive thing in a noble gas, and it'll just sit there because it can't react with the noble gas. The noble gas won't let it do anything.
Nobody wants to play with me. They're stuck up.
With the exception of xenon. Yeah. For some reason, xenon, but not radon, even though it has more electrons that are further away from its atom, xenon will do some very slow reactions.
Is he really persuaded?
It's nowhere near anything else on the periodic table, but it is far more reactive than any of the other noble gases, because anything is a lot bigger than nothing. So that is the main things, the things most people are concerned with. And we'll actually talk about in any science course up to like high level university. Now we got lanthanides and actinides. I don't know fucking anything about those because, like I said, high level university, I ain't there yet. I'm finishing my fucking bachelor's degree in chemistry this year. Like, I don't fucking touch those.
We don't talk about those.
The most I know about those is that they explode.
Aren't they radioactive too? It's
Yes.
like uranium on there, plutonium.
These are the radioactive explodey elements. Chuck enough of them in a small enclosed space together, and it'll melt your face.
Demon core.
The demon core. But yeah, so like you said earlier, there's thorium in here. And then you also got uranium and plutonium. And those are the three main things that are in nuclear reactors. Well, not thorium yet. It's mainly uranium and plutonium that we use in nuclear reactors. But there is actual research going into using thorium because thorium produces less radioactivity than uranium and plutonium. And it's also harder to make a thorium bomb.
Oh, okay.
Yeah.
So we don't have to worry about that as much.
Yeah.
Where's radium?
Radium? Where the fuck is radium? I don't know. It's somewhere. I think... No, that's radon. No, that's radon. That's radium.
That's radium.
It's the bottom of the alkali earth metals.
Right.
And then there's this very special section in black. That is the physicists pretending to be chemists section. So, as I said earlier, the entire thing that an element is how many protons it has. So, like, carbon has 6. Helium has 2. So, as you can imagine, we got to the end here. For a long time, this was the heaviest element we know. Don't ask me what it's called. I have no fucking clue. It's HS. It's for the longest time. But there were some people who thought, well, if an atom is defined by how many protons it has, what if we just add more protons? So we got big, massive particle accelerators, put a sample of this in there, and just flung protons at it so fast that eventually they'd stick to the atom, and we started getting this, and then that one, and then all of these new elements that don't fucking exist because physicists make them for a split second, and then they decay and split off into smaller, more stable atoms.
I do not vibe with this universe.
They do not vibe with this universe. They do not want to be on this plane of existence. The heaviest one is oganesson. It's in the noble gas category, but it is not a noble gas because I think the longest they were able to make oganesson exist for was less than a second. They made it, they proved that they made it, and then it just peaced out. So, yeah. That is the periodic table of elements. One last thing. The reason it's structured like this, because you might think like, why is hydrogen over here and not over here, and why doesn't everything just get moved that way or moved this way? So that if you want all the full shells to be on the left, just slide everything that way. Number one, it was the trend, like keeping the alkali metals together. Very nice. It makes it easy for undergrad students. Another thing, however, are orbitals. So the classic model of the atom, it looks like this. You have the nucleus in the middle with electrons on the rings around it, orbiting the nucleus like planets orbiting a star. But that's not really how an atom is.
That's just an easy way to think
Yeah,
of it.
it's an easy way to think about it. It's a way to present the atom to high school and first-year university students without breaking their brain.
You don't want to break your brain yet.
No, not yet. That comes later. Electrons are so small. They are actually what is called quantum particles. And just saying quantum might get some of you fucking having an aneurysm, but calm down. Quantum literally just means really, 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 really small. Electrons are one of the smallest particles we know of. Because of this, because of their property as being quantum particles, they don't really exist in a single point. They do, but not really, because at that small scale, matter also starts behaving like waves. So instead of an atom with a nucleus and electrons orbiting it, you have an atom with a nucleus and then a cloud of electron density probability of where the electron might be. And those clouds are split up into what's called orbitals instead of orbits.
They get funny shapes.
They do. Well, not the first one.
Yeah,
The first
ball.
ones are just a sphere.
Orb. Orb. Me pondering my orb.
So they're split up into orbitals of shell numbers. So like the shell 1, shell 2, shell 3, all the way down. And then the shells, so the orbitals are in the shells, and then the orbitals are split up into S, P, D, and F orbitals. So that doesn't mean anything. It's just they wanted to assign some name to it. So Sphere. S for sphere. Not really. They just had to give a name for it, and whoever discovered it just decided to make it easy and do letters. So S comes first. The S orbitals can only hold 2 electrons. I may get into why in another video, but I'm already talking about too much shit and probably going too long here, so whatever. S orbitals can only hold 2 electrons. So you may notice these two guys before the transition metal starts. That is because these are the 2 columns that fill the S shell last. So you get the first electron in your s orbital in this row, and then the second electron in your s orbital in this row. Technically, by that logic, helium should be over here because it fills the second spot in the s orbital and then it's full. But since it's full, that overrides it and it's over with the noble gases.
It acts more like a noble gas anyways.
So lithium then fills 1 electron in its second s orbital. Beryllium fucking hate my life. Beryllium fills the next electron in its s orbital, and now its second s orbital is full, but the second shell can still hold more electrons. So rather than making another s orbital, it starts filling p orbitals. S orbital was shaped like a sphere. It's close to the nucleus. P orbitals are shaped like a peanut, where a lot of the electron density is actually kind of far out from the from the atom. And so the p orbitals can hold 6 electrons. So we got 1, 2, 3, 4, 5, and then 6. And then you got full p orbital, full shell. And then same thing with the next row. Fill the s's, fill the p's. Everybody's happy. And then you get down here, transition metals. This is where you start filling the d orbitals.
I don't know what D is for. D is just weird.
It's just weird. It's a weird shape. I can't really describe D and F.
It's like a donut one.
Yeah, no, it's not really. Not at all.
It's like a donut. Isn't that
maybe one of the configurations is?
Maybe.
I don't know. We got transition metals are d orbitals. Lanthanides and actinides are f orbitals. Same shit, different story. You can fit 10. You can fit
Frickum.
14. What?
Is it because frickum?
Because fuck.
Okay. Demonetized. That's what
I
the
think
D
I was
orbital.
making money off this shit. I have like 6 subscribers.
Nice.
But yeah. So that's orbitals.
Right.
And that'll end it. And don't fucking ask about chromium and cobalt because they're weird and they make chemistry hard.
Okay.